you have questions, you should ask one of us, preferably not David. So David will say some things about the bands this evening, but I should remind you that we have the evening sessions in the hotel starting at 7:30, and the room is reserved until 1 a.m. And I hope you all use it even later. As most of you are new here, you may know that this is very intense, and you are actually encouraged, even if you're not part officially of the group that is going to be doing a presentation on Wednesday, to join any one of those groups that you would like to work with and participate as much as you like. The fact that you're not officially attached to the group doesn't mean you cannot just join and chip in, and you should. I should say that these sessions can be very, very well, apart from intense, very useful. And there's been, at least in the latest count, about 20 papers that arose from during that at the Alternative School. And I don't mean this as an intimidation, rather than as inspirations. So use your time as profitable as you can. I think I'm sure you will. A lot of people are going to start complaining about power strips, which we don't have today, but we'll hopefully have tomorrow. There's only a few places in this room to plug in. And David, you had something about it. There is, in case you're wondering, there is no change in daylight savings in Arizona. So if your computer says a different time, it will still be the same time on Monday here as it is now. So make sure you don't get confused.
So there have been issues with, say, iPhones getting it wrong briefly, so do be aware that there is no time change here.
Okay, I think that's all I have to say.
Okay, how is this? This is okay.
Actually, sorry.
Okay, so this is working now. Great. So I just wanted to talk a little bit about the transportation, both in the mornings and in the evenings. So first with the mornings, first of all, we're glad to see that the hotel actually got everybody here. Now I know that they very zealously told you all that you needed to be out there at 8 o'clock at the latest in order to get your shuttle in. But our goal is really to make those shuttles as unobtrusive as possible for you. Transportation will start leaving at 8, and the last buses will leave at around 8:30. You should feel free to kind of show up at your leisure in that half-hour period. Of course, don't everybody show up at 8:30, because then it will be an unpleasant rush at 8:30. So if your natural tendency is to kind of come out a little earlier, please do. So that's what we'll try tomorrow, and if that works, then that's what we'll keep doing. In the evenings, there are 2 sets of shuttles from the university area back to the hotel. First of all, right after the lectures, there will be buses and shuttles ready to take people back. But you might want to have dinner around the university. And for those of you who do, there will be shuttles leaving from a parking lot at Tyndall and University. So yeah, there's great, right, perfect. So it's where this little bus is marked on here. So we're here, and this street over here, University, has a lot of restaurants. So you might want to eat there and then come and catch a shuttle at 7:15 here. I know that's early, but it's designed so that people can get back for the working sessions at 7:30. If you stay out late, there's a phone number. You can call the main switchboard at the hotel. You're sort of taking your chances of whether they'll have shuttles available for you. But you can call to try to arrange a shuttle afterwards. So if there are any questions about how that's going to work, you should feel free to. Well, if there are any pressing questions now that you think are important.
And this, of course, is on the website. You can find it.
Right. So is there any confusion now? Okay, great. So then I guess we're ready to start. So. So let me then turn it over. Are you ready? All right. Okay, so let me turn it over to Robert Pollack from Boston University, who will talk about overconvergent modular symbols.
Okay, am I mic'd okay? Can people hear me? Is it coming through? You can't hear me. Okay, so mixed answers. I will. Okay, so this set of lectures will be on overconvergent modular symbols. Overconvergent modular symbols are kind of fancy versions of modular symbols. They take values in these large infinite dimensional spaces of p-adic distributions, and they're kind of really great. They really have all these great applications, like you can, they're intimately related with modular forms, overconvergent modular forms. They have the right systematic eigenvalues. You can construct eigenvarieties out of them. You can get p-adic L functions. You can get families of p-adic L functions. And with that all said, the kind of goal of these lectures in some sense is to show you that these are really down-to-earth concrete objects, that despite their fancy nature and their fancy definitions, you really can get your hands on them. And that's kind of the goals of these lectures, is to try and show you that one can really explicitly understand overconvergent modular symbols, so much to the extent that you can put them on a computer and compute with them. Although I won't be doing that in the lectures, we'll be talking about some algorithms of how one can do that. And with that said, that's part of the reason why these series of lectures are part of this conference. To compute star-Kigner points, one method of doing it is to use moments of p-adic L functions, and to compute moments of p-adic L functions, you use overconvergent modular symbols. So that's why we're here. I'm actually not going to talk about star-Kigner points besides that sentence in these lectures, just on overconvergent modular symbols. Okay, the basic structure of the lecture series. This morning, I'll talk about classical modular symbols and try to convince you that they are very concrete objects and just things that one can really get your hands on. This afternoon, I give a second talk. There I'll introduce the spaces of p-adic distributions that you use to define overconvergent modular symbols. So we'll go through that in a very concrete way. And then the next two lectures will involve proving theorems about comparing overconvergent modular symbols to classical modular symbols and relating to p-adic L functions and families of p-adic L functions. So that's the plan. So right now, let's just start with classical modular symbols. And to do that, I want to give a motivating example of where they come from, namely from period integrals of modular forms. Can people read that? Is that large enough? Okay, great. So let me fix a cusp form. Let F be a cusp form of weight 2, let's say. On, let's fix a level, let's say gamma 0 of n. And then the period integrals that I want to think about, well, that's just a constant or normalized thing. So I'm going to integrate from R to S f of z dz, where R and S are some rational numbers. So R and S are in Q, or maybe they're infinity, so let me say P1 of Q. And what I mean by this integral, here's my R, here's my S, and I mean take the kind of semicircle joining them, sort of G at S like in the upper half plane. And you do the line integral over that curve. So if one of them is infinity, then that's interpreted just as a straight line from the rational cusp together. And so these are the period integrals, and I first want to try and convince you that they're actually quite interesting values. You know, I'm wondering why one writes down those integrals, but at least try and motivate them by saying that they have very interesting information encoded in them. So here's the first formula that tells you great things about period integrals. If I do this integral from infinity, I'll write infinity is I infinity, to 0, that's integration along a vertical line of f of z dz. That's an L value. That's the L series of f evaluated at 1. So here the L series, I mean the sum of a and n to the s, where those a n's are the Fourier coefficients of the modular form. So a n q to the n, q is e to the 2 pi I z. Is my writing getting too small? Oh, I'm still getting okay, so that's great. Super. So that's one formula to try and convince you of the interest of these period integrals. They know an L value of an L series. That's great. In fact, I'm just integrating along one path. That's one period integral. If I look at a collection of all period integrals, it has a lot more information than that. It actually has all the twisted L values. And this should be a formula like this. So let me take a Dirichlet character. So I can do twists. So let chi be a Dirichlet character. Probably. Where? Is it 2 pi? What? Which in this one? I can't look and use my. Wait, which integral?
Yeah, there.
I shouldn't have that 2 pi.
Oh, sorry.
Okay, I can. So you can look at the twisted L series. So let me write that as L F chi S. So what I do is I just take the Dirichlet series, this one, and rather than having an, I have an chi of n. So this is the sum of an chi of n over n to the s. I'm getting to the bottom. Let me scoot this over. Then here's the formula. The twisted L value at 1 is some constant, I'm not going to say, it's just some kind of Gauss sum of the sum over A modulo n of 2 pi I, chi A, 2 pi I, integral from infinity to A over P to the n, f of z dz. I think I'm getting that right. So if you take a bunch of the period integrals and take the appropriate linear combination of them with the values of the character, then you pick up the twisted L value. What am I writing? Well, okay, ultimately I'm going to have a power of P, and so that was just not A over n. I'm summing over the numbers modulo n, and then I integrate to A over n. So the collection of all period lattices knows all the twists of the L functions. And if you haven't seen any of these L value formulas before with the period integrals, I thought I would give at least a completely bogus argument to try and convince you of it. There's convergence issues in this argument, but they can be made to work out. So here's a kind of a heuristic, at least. I want to compute the integral from infinity to just to 0 of f of z dz. So then I write the modular form by its Q expansion. So an e to the 2 pi I and z. And then I switch the integral and the sum, hopefully. And so then I have a sum, and then I do out the integral, and then I integrate the e to the 2 pi I and z. That 2 pi I goes away, and I get an, so an over n e to the 2 pi I and z evaluated from 0 to I infinity. And then at 0, this function is just 1. At I infinity, it vanishes. So that's the sum of an over n, and that's LF of 1. You just plug in one formula into the Dirichlet series. But there are problems. I think that series doesn't converge at 1, and even though the switching integral, there's lots of problems with that argument, but it can be made to work. You kind of put in a z to the s, and then maybe a gamma function appears, and you do it out correctly, and then that's there's something in that argument. It's not just completely vacuous. It's the reason why this kind of things can be true. And okay, so I hope that at least these little bits of sentences convince you that period integrals have some interesting arithmetic data inside of them. Next thing I want to point out is there's a lot of, well, before I even say what the answer is, I wanted to do a numerical experiment, at least maybe a thought experiment. So I want to fix a particular modular form. So I'm going to take f of z to be in weight 2 level 11. People don't know the numerology here that if you look in forms of weight 2, on SL2Z, there are no cuspidal forms. But if you begin to shrink down SL2Z to congruent subgroups, the very first time you encounter a cuspidal form is when n is 11. That's kind of this first example. Take F to be, a normalized new form in that one-dimensional space. And then, let's compute these period integrals, because I should still have my 2 pi I, as you run over R and S. Take 100 random values of R and S for a bunch of R and S's. And then you just imagine going to a computer and just approximating those integrals, and you get a bunch of complex numbers, and then you plot them in the plane and see what you get. So let me show you a picture. This will be the only graphic of the talks. Low tech. So those dots are the period integrals that you get. So if you haven't seen it before, it's shockingly regular, right? It's a lattice. It's like a lattice. So those random complex numbers are not so random. And I should admit there's some lies going on here. In fact, I didn't integrate over any two R and S's. I only did ones that were gamma 0 of 11 equivalent. So they were from the same cusp. Otherwise, it would be a slightly different picture. And in fact, in fact, you probably don't get the full lattice. You have to take the span of what you get, and then you get a lattice. But it's still kind of remarkable that there's all this algebraic structure to the period intervals. And that's where modular symbols come in. Modular symbols are supposed to be kind of an algebraic, an attempt to algebraically formalize what's going on. It's the algebraic structure of the period integrals. So let me get to that. Modular symbols. So let me give you a definition. So let me let delta 0 be degree 0 divisors on P1 of Q. So a typical element there looks like just the difference of two rational numbers, S minus R, and then you think of that to sort of relate to the previous discussion. That's like the path connecting R to S. And now, given a modular form, so back in general, F is just some cusp form, I can make a function, say psi sub F, from delta 0 to the complex numbers that sends a divisor like this to the period integral. And I'm only telling you how to do it on the special divisors that are the difference of two things, but for a general divisor, it's just the sum of those things, so then you extend it linearly. And so that gives rise to an element of an additive homomorphism from degree 0 divisors to the complex numbers. And an easy fact, I'll say a second how to check it. If you do one of these period integrals from R to S, or you take a matrix, let's say gamma, in gamma 0 of n, that's the level of the modular form. I should write that somewhere. So F is way 2 form on gamma 0 of n, cusp form. And I act by linear fractional transformations on the endpoints. I don't change the integral. And so here, gamma of z is az plus b, cz plus d. Standard linear fractional transformation where that's the matrix. I'm not on the screen anymore. And I say it's an easy fact, it really is. You do a change of variables, and then you use the modularity of f. And exactly the modularity of f cancels with the change of variables that you do. You could give this exercise to like second semester calculus students, I guess. Probably not, actually. Okay, and so I in fact, I don't just have a homomorphism. I have a homomorphism with a gamma invariance. So this fact here implies that my function psi f, if I apply it to some divisor, so here d is in delta 0, then this is the same as acting on the divisor by linear fractional transformations on all of the entries, because it's just built out by these integrals that have that property. And so this is telling us that, in fact, this function, I would say, is in a smaller collection. It's not just a homomorphism, it has a gamma 0 of n invariance. So I'll use that subscript to mean exactly this property here. And this here will be our space of C-valued modular symbols with level gamma 0 of n. And what we've done is we've made a map from cusp forms of weight 2 and level n into this space of modular symbols. just by sending the form to its associated symbol. And what's neat about this approach is that this space is defined, using complex analysis and Q expansions and homomorphy, where this space here is just defined purely algebraically, right? Everything there is just algebraic. You don't need to know any complex analysis to write down this right-hand side. So, and I should say there's a little bit, more structure going on here. In that case of the modular form of level 11, we saw that period lattice appeared. So there's sort of 2 dimensions of data going on. And so somehow this modular symbol is carrying 2 pieces of information. So it'd be nice to sort of separate out the 2 generators of that lattice. And you can do that. There's an involution on the space. So there's an involution, so iota, on the space of modular symbols. Just defined like this, if phi is some random modular symbol and I want to apply iota, I have to tell you what that does to a divisor. And I just act by this matrix on the divisor. And that's clearly order 2. And what is this matrix doing? This is sending a divisor like that over to just negating it. Like this. And so whenever you have an involution, then you can uniquely decompose the modular symbol into the plus part and the minus part, just the eigenspace, the plus eigenspace and the minus eigenspace. And if you do that, that really separates out the period lattice. So for example, going back to the gamma 0 of 11 example, I have that form F, and now I can attach 2 modular symbols, the +1 and the -1. And this putatively took values in C, but in fact it takes values in integral multiples of some complex number, which is one of the generators of the lattice. And the other one takes values in corresponding thing in another period. So these are just the periods of that lattice. So I was writing down. And so in this map here, over on those slides, I have modular form sitting inside of here, but I have 2 copies of the modular form, one for the plus and one for the minus. And then those are the two symbols here. And you ask, is there anything else in this space? Am I getting anything more? This space is algebraically defined, but maybe it's like 1,000 times bigger than this space, in which case you're really not capturing stuff. You want to sort of say that you really can cut out the modular forms that are inside of here. So you ask, what else is in? Anything else? Besides these 2 symbols. And in fact, yes, there's a much easier way to write down a modular symbol. And now that we have this algebraic description, I'll just write down something else for you. It doesn't involve any modular forms on the surface. So here's an easier way to build symbols. Let me let delta be just divisors on P1, not degree 0. And then I could look at gamma naught of n invariant functions from delta to C, and then of course I can map that to the space of modular symbols just by restricting. And so if I can make something here that doesn't restrict to 0 here, then I get a new symbol. And what does it mean to be an element in this space? That's just saying that I'm a function on the cusps that's invariant under gamma 0 of n. So I'm a function, so phi in here, this is a function on P1 of Q. Right? I mean, if I tell you what it is in divisors, I could just tell you what it does on every element of P1 of Q. That's constant on the orbits of the action by linear fractional transformation of gamma 0 of n. That's the cusps of the modular curve. I don't know when n transferred into 11, but if you just, 11 and n are really close, you just have to connect the line when I'm making that mistake. And so in this example, if I look at P1 of Q and I mod out by the action of gamma 0, 11, you only get 2 orbits. There are 2 cusps on the modular curve of level 11. There's the infinity cusp and there's the 0 cusp. Namely, this breaks up into infinity and 0. And this corresponds to all the fractions that look like a over 11c. And this is a over c, where 11 doesn't divide c. Am I still on the, oh no. So if I act infinity by any matrix in gamma 0 of 11, the answer necessarily has 11 in the denominator. And in fact, any fraction of that form can be transformed from one to another by gamma 0 of 11, and the same is true for the zero cusp. And so an element here, that's just a two-dimensional space. I just have to say, what does it do to infinity? What does it do to zero? And then you extend it by constantness on the rest of the orbit. Okay, so this is telling us that. So now gamma 0 of 11, I really mean 11. Oh, I didn't mean that though. Oh no. Just delta, not delta 0, just all, just divisors, not degree 0. This is two-dimensional. And you could write down what the, here's one symbol. I say that it's 1, so on x, if x is equivalent gamma 0 of n to infinity and 0 otherwise. And then I could do it the other way. Those are the two, those span the space. And notice that there is a kernel to this map, the restriction map from just divisors, degree 0 divisors. If I have a function that's constant everywhere, then that just dies on the restriction map. So there's a relation between these two symbols. So after I restrict, if I take phi naught and I restrict to degree 0 divisors, that's equal to the minus of that, because the constant function becomes 0. And so in fact I get one new modular symbol. Get one new modular symbol. Just either of those two. And you say, okay, well, I can actually, if I get one, I can get two. I just decompose it into its plus minus parts, like we did with the period lattice. But it doesn't work, because if you just look at it, this symbol that you get is even. It's in the plus part, because the way, it's no longer up there. The way you break up into plus and minus parts is you have to negate the cusp. But if you negate the cusp, you're still in the same equivalence class, so it doesn't change the symbol. So it's a plus symbol. So that's it. So that gives us now then that this space, when I put the 0 back, this is really an 11, is at least three-dimensional. And you can ask again, any more? Okay, so there's only one cusp form of level 11, and we already got the modular symbol attached to that. It's not. It's not. Well, I mean, yeah, it's not. You just write down the other one. It's not. It's probably a better answer than that, but you can just check it. It never can be the same. Yes, yeah, it's not. Okay, so to ask if there's any more modular symbols in there, just ask the question, what does it take to determine a modular symbol? So let me step back into more generality, go back to some general level. Let me just call it gamma 0 of n. So what info determines a modular symbol? Yes. So far we've been like building symbols. We found 3 dimensions of symbols. Now we're to the other end and try and get an upper bound on them. Try and meet somewhere in the middle. And so, modular symbol is a function on delta 0. So, okay, you have to give a value for every element of delta 0, but it's enough to just give a generating set of delta 0. And of course, this is generated by the symbol divisors, s minus r. So I just have to give you information about, just as we did before, just pairs of rational numbers. And then the next claim to make, to sort of cut down more, so the collection of differences like that is generated by more special differences of rational numbers, things of the form by divisors of the form b over d minus a over c, where these numbers actually give an SL2Z matrix. So this is the determinant condition, AD minus BC is 1. This is what I would call a unimodular path. So what I'm saying is that anything like this, if I have two rational numbers that don't satisfy that, I can sort of put in a bunch of rational numbers in between them that do, and that link them up. If you haven't seen this before, this is the continued fraction algorithm, Nines continued fraction algorithm. So let me prove this by example here. I wrote something in my notes here. Let's say I start with that is my S and that is my R. So that doesn't satisfy it. That determinant is 11, but I can write it like this. So 11 over 4 minus 3 over 1. That one satisfies the determinant condition. And then I add back that 3 over 1. And I subtract 2 over 1. And now that doesn't satisfy the determinant condition. I'm getting minus 1, but I could just put in minus signs. That fixes that problem. Okay, and then I add on 2 over 1, and then I subtract away 0 over 1. No. 1 over 0. That satisfies it, and then I have to add on. 1 over 0 is infinity, minus 0. That's a mess. Sorry. Anyway, those are the continued fraction convergence of 11/4 connecting to. So you can always do that. That's the reason why it suffices. Rather than looking at general divisors, I can look at these unimodular divisors. And so I can really think of the modular symbol, rather than being a function in this very large space of degree 0 divisors, as being like a function on matrices. So given alpha and SL2Z, say ABCD, let me use the notation bracket alpha to be B over D minus A over C, the corresponding divisor. And so to determine phi, a modular symbol, so phi is determined by its values on bracket alpha for all alpha. And so far, all I've used about the definition of the modular symbol is its additivity. I still have its gamma invariance. And so the gamma invariance of phi implies that, in fact, phi of bracket alpha only depends on alpha in as a coset in SL2Z mod gamma 0 of n. Because the condition was if I act by a matrix on the left of the divisor, I get the same value. And that translates in this language just multiplying by the matrix. So it only depends upon multiplication on the left by gamma 0 of n. And now we've really done something, because this is a finite set. So in fact, the modular symbol is only determined by finitely many values. It's not this sort of monster of a space of all degree 0 divisors. And moreover, it's a really explicit set. So SL2Z mod gamma 0 of n can be put in bijection with P1 of Z mod NZ by just sending a matrix to the bottom row. I think that's how I want to normalize things. Just meaning, if you change a matrix by multiplication on the left by something in gamma 0 of n, it doesn't change this as an element of P1. It just scales it. And so back to our example of n equals 11, we know that the space of modular symbols is at most 12-dimensional. Right? Because P1 of Z mod 11Z has 12 elements in it. So now we're somewhere in between 3 and 12. But there's more. I mean, like, it's not 12, it's 3-dimensional. So we really found them all. And you can keep on going. There are more relations that I haven't written down yet, you also have these other relations. So note, if I take the matrix ABCD and its corresponding divisor, or I take the matrix, and I did this trick when I was writing down the continued fraction stuff, minus B minus D, AC. As divisors, these are just negatives of each other. Like this one is B over D minus A over C, and this one is A over C minus B over minus D. So it's like, if you think in terms of the path, this one is the path going this way, and this one is the path going the other way. So that's a relation on the values of the modular symbol when you think of it as like a function on P1. So I'll use notation and write it this way. Phi on an element of P1 like this is minus phi on that. And what I mean by this, I really mean, okay, complete that to any matrix in SL2Z, think of the corresponding divisor, and evaluate the modular symbol on that, and it's independent of all the choices. That's what the previous argument's all about. And so there's a relation on those values on P1, and then there's another relation I'll just draw geometrically, the triangle relation. If this is A over B, and this is C over D, then like the Faraday fraction between them, A plus C over B plus D. Note that those are unimodular. The determinants here are 1. And so you have a 3-term relation, because when you go around that triangle, you get 0. By adding this divisor to that divisor to that divisor, you get 0. So that's a 3-term relation. That's a 3-term relation. And these two things taken together are commonly referred to as the Monin relations. And then you could just, I was trying to, I made the speech at the beginning, I was trying to say that these are explicit things. You can just do this. You just enumerate the elements of P1 of Z mod 11, and you write down what these relations are, and you kind of just figure out what functions are on them that satisfy these relations, and you do that computation, and you see that you have at most 3 dimensions. So then you have exactly 3 dimensions, because you already wrote down that thing. So solve the relations. And you get that. The modular symbols over gamma 0, 11 are 3-dimensional. Okay. That was just weight 2. I also want to talk about higher weight modular forms. To do higher weight modular forms, the only difference is you have to allow for non-trivial coefficients for the modular symbols. What I have set up now is just modular symbols with complex coefficients, and those complex coefficients have no action on them. So I want to put a non-trivial modulo there. So before I do that, let me just set things up in general. So you need non-trivial coefficients. So let me let V be some abstract Z bracket gamma module. Here gamma is some congruent subgroup. And I can look at maps from degree 0 divisors into V. Additive. Additive, that's what the hum means. And I can give this space an action of gamma. Actually, it's going to be a right action. Defined as follows. For phi in here and gamma, I act gamma on phi. And I'll define this for you. We'll have to tell you what it does to a divisor. And so by definition, this is going to be phi acting on gamma of D, then acting on the space outside by gamma. This is a right. V is a right Z bracket gamma module. Why these conventions of right and left, they're going to crop up all over the course. I'll discuss them more in the next lecture, rather than doing it all now. But this is how I want to set up the formalisms. You put in right modules, and then this becomes a right module under this action. And then to be a modular symbol, you ask that it be invariant under the action. So then the modular symbols with values in V and level gamma equals the that subscript of gamma just means the invariant map. So explicitly, this says that phi stroke gamma equals phi, which if you convert that out, that means phi of gamma d is phi of d stroke gamma inverse, the inverse that appears. And so if you take the case where v is just the complex numbers with no action on it, then this goes away, and that's exactly the same definition we had before. And then let me just tell you what the v you take to get higher weight modular symbols. You take symmetric powers. So take v equal to, I'll call v sub k, which is sim k of c squared, which I want to think of as homogeneous polynomials in x and y of degree k. And I need to tell you how gamma acts on that. And so it's a representation, has a gamma action. Again, the normalization might be a little funny. If p is an element of sim k, I want to act it on the right by gamma. The way I'm going to do that is by acting on the right on the variable by the adjugate matrix. So sorry if that's not the action you wanted to see, but it works. So this gamma star means dA minus b minus c. And if you act on the right, then you're getting a left action, but if you put the adjugate there, then you get back a right action. Why these normalizations? Okay, that's what they are. And then I'm going to write down a map for you from weight k plus 2 modular forms. So I take cusp forms of weight k plus 2 on gamma, and then I'm going to give you a map now to modular symbols with values in vk, values in sim k. So note, there's a shifting of the index here, which is to be expected because weight 2 modular forms went to sim 0. So I have, again, a nightmare of notation. Do I call this k or do I call that k? So right now, apparently, I'm calling that k and this k plus 2. I'm going to keep messing this up throughout the lectures. And what's the map? I just take a modular form and I send it to, well, I have to tell you what it does to divisors. So I'll tell you what it does to these simple divisors, which are just the difference of two terms. And it's going to go to some period integral. So I integrate from r to s. Probably should have a 2 pi I. And then I do this. I integrate zx plus y to the k of z dz. Here the x and y are just indeterminants. So that really means is binomial will expand out, and then you formally integrate each coefficient. And then you get an element in sim k, and the coefficients are all integrals of the form, some binomial coefficient, z to a power f of z. And this is not unexpected because when you have a modular form of weight k, its L values, they're more critical L values. It has k minus 1 L values that are critical, and they come from integrating z to a power f of z, where that power goes between 0 and k minus 2. Let me call this as before, psi f. And with all the normalizations I wrote down, and you can check this for yourself, it's not a hard exercise. If I evaluate a divisor acted on by gamma, then that's the same as just evaluating at the divisor, except that all of those x and y's get mixed around, and they get mixed around exactly by this way, acting by gamma inverse. That's the condition that says that, in fact, this is invariant under gamma. It's in there. And the second thing to point out is, I was saying about L values, if I evaluate on that divisor, well, then I get an element of sim k, so it looks like that, and this coefficient, this ci, I won't write down the exact formula, but it's related to the L value of f at I plus 1. So you get a bunch of L values. Okay, great. So now we have a formalism. As before, this is this, and again, we have the involution on this space, and we're going to get 2 copies of this space inside of here, plus maybe a little bit more from the boundary symbols that we're writing down on just divisors. And I'm really touting this is great because this is completely algebraically defined, where this has all this complex analysis. But in fact, at this point, it's a little bit useless, everything that I've done, because these are just vector spaces, how I'm writing things down. And so I have to algebraically define some vector space. So all I'm kind of capturing is the dimension of the space. But we care about so much more for modular forms than just how many there are. Right? We care about the Q expansion, their Fourier coefficients, the Hecke eigenvalues. So to make sense of this, you really need a Hecke action here. But don't worry, that's fine. There's a Hecke action on modular symbols, and it's equivariant for everything that's around. So there's a Hecke action. Namely, if I look at this space of VK valued modular symbols, I can define, like in the case of modular forms, Hecke operators Tn by a double coset. So gamma, the double coset of 1, 0, 0, n. Which I mean, you write that double coset as a union of single cosets, and then you act each of those matrices on there, and that preserves the level, and you come back again. But I can write this down completely explicitly for you. If I write down gamma to be gamma 0 of n, and let me let L be a prime not dividing n, then a modular symbol acted on, Hecke acts on the right, even it does that for modular forms too. If I act on phi by the L Hecke operator on some, I don't have to tell you on a divisor, I just tell you as I act on matrices, I just sum from A from 0 to L minus 1 of phi acted on by 1A 0 L plus phi acted on by L 0 0 1. Just like for modular forms. And the key fact, and it's not hard to check, is that the association from F to the modular symbol psi F preserves Hecke. Meaning I could take my modular form and act by Hecke and then look at the associated modular symbol, or I could take the modular symbol and then do this definition of Hecke and you get the same thing. So this map here is a Hecke equivariant map. So we're keeping track of everything in this purely algebraic framework, which is that's the great part. And let me state the formal theorem that kind of summarizes all the numerical stuff that I've been sort of pitching during the talk. It's the Eichel-Schmürer theorem. What? Oh, I didn't switch slides, sorry. So yes. So Eichel-Schmürer states the following: there is an isomorphism of Hecke modules between modular forms of weight k plus 2 plus cusp forms of weight k plus 2 and these VK valued modular symbols. Remember, VK is just sim k. And that's what we saw in the gamma 0 of 11 example, where we had two copies of the cusp forms, that's here and here, and then we had one extra symbol. And that's coming from the fact that I, my cusp forms here, I wrote modular forms. So there's an Eisenstein series that's accounting for that. So some remarks. So this space has this involution that breaks it into plus minus parts, and the plus part corresponds to this. So mk plus 2 gamma corresponds to the plus part. The sk plus 2 gamma here corresponds to the minus part. And the Eisenstein series here, the Eisenstein series that are not, the difference between this space and the underlying cusp forms, that's entirely corresponded for the boundary symbols. I just mean the ones that come from delta, not delta 0. And it's a great exercise to go back and look at that boundary symbol that I wrote down for you for gamma 0 of 11, and look at the Hecke action on it, and write down the Hecke eigenvalues that you get. And you see is that TL acts by multiplication by L plus 1. So that boundary symbol is somehow Eisenstein. That's what it means, the isomorphism of the Hecke modules. It really has the right Hecke eigenvalues. And let me finish up with one more remark. So I mean, I've been saying it, let me just write it down. The right-hand side of this isomorphism is completely algebraic. And completely computable. You go through that same method that I was sketching when we were doing the upper bound on the space of modular symbols. A modular symbol is determined by its values on unimodular paths. And that's determined by its values on SL2Z matrices modulo the action of gamma 0 of n. So you just enumerate those spaces. And then you have the Monin relations. It's just linear algebra. You solve the Monin relations, and then you can work back up and completely describe what the modular symbols are. The well-known algorithms that date back to the 70s that are now nicely coded in like Magma and Sage and all those packages. And that's the fact that it's computable. The fact that it's completely algebraic, VK, this is sim k of c squared. Now that I have a completely algebraic description of things, I can replace this with maybe sim k of q or sim k of z. And the right-hand side will still make sense because those matrices all act on these things. So now you suddenly have rational or integral structures involved. In fact, knowing this gives you a proof of the fact that the Hecke eigenvalues of a modular form are algebraic integers. Because this has, instead of VK, I use this module, and then I tensor up with C, that's the same thing. And so I have a basis to find over Z, and so then these Hecke algebras find over basis. So it's quite nice. And we're already over time, so let me stop here, and then on the afternoon I'm going to now pick up, and rather than just replacing VK with these small spaces, we're going to replace VK with an infinite dimensional Banach space with p-adic distributions, and that will let us have overconvergent modular symbols rather than classical modular symbols. Thanks.